when you understood the fundamentals about the continuity equation, there's basically only one statement of the continuity equation, isn't it? That mass is conserved. Then you learned or knew about the first law of thermodynamics. And really, even though you have a closed system model and an open system model, there's really only one statement of the first law of thermodynamics, isn't it? Energy is conserved. The second law of thermodynamics is a little bit different, and there are what we want to cover is three statements of the second law of thermodynamics, and each one of them has a lot of power unto itself. So let's go ahead and get started. So I've marked this section important because it's three statements of the second law of thermodynamics, and that's the title of your chapter. And so, again, we're still building on getting ready to solve problems complete with numbers and units. But the statements of the second law of thermodynamics is really the foundation of our ability to solve problems. Have folks told you along the way that anything is possible? They grin at you, say, anything is possible. If you can dream it, you can achieve it. And, there's a lot of truth to that to some extent. But you don't want to get carried away, do you? And so I really like this little image of our friend Lee Corso, who's retiring in 2025. So when anybody tells him anything is possible, if you can think it, you can make it happen. So not exactly. And Lee Corso is famous for saying, "Not so fast, my friend." And we're going to miss him saying, "Not so fast, my friend." But truer words have never been spoken. Let's go through another mental exercise. Would you say it's possible to build and operate an electric power plant? Would you say that's possible? I'd say it is because you're looking at one on your screen. This is the John Amos electric power plant in West Virginia. And so what's it doing? It's transferring heat transfer, a high temperature heat transfer by combining fuel and air into very high temperature exhaust products, transferring heat transfer into electric power. So yes, it is possible to build and operate a power plant. Is it possible to buy and run a refrigerator? I think it is because you can see refrigerators with your eyes. You can experience them. You depend on refrigerators. And then you start thinking about your thermodynamics class and you say, now, well, wait a minute. I thought this guy was telling me, instructors were telling me, um, uh, there's some trick. We're transferring heat from a cold space to a warm space, aren't we? With a refrigerator, we're taking heat away. We're rejecting heat from our cartons of milk, from cheese, beverages. We're rejecting heat from them, and we're pulling heat from them, and we're sending the heat into the kitchen. Basically, behind the refrigerator, heat's being rejected behind the refrigerator. And so you say, well, wait a minute. I was told that heat only flows from hot to cold. And that is true, but heat only flows from hot to cold on its own. And so the trick of the refrigerator, so the genius of the refrigerator is recognizing that you can transfer heat from cold to warm at the price of having to do work. And that's the key. So, of course, we can buy and operate a refrigerator, but we have to invest electric power. It costs us some money to run a refrigerator to transfer heat from cold to hot. And that's another big recognition that you, as an engineer, you've already got that figured out. Well, that introduces the three statements of the first law. And so the first law I'm going to read the clip out of your textbook, the Clausius statement. So this would be called the first statement, state one of three statements. And it says, here's what the words say. It's impossible for any system to operate in such a way that the sole result would be energy transfer from cold to hot. That makes sense. Okay, if you dissect those words, it says the sole result would be heat transfer from cold to hot. Okay, and so I've tried to draw that schematically so let's look at the left-hand schematic. Okay, it says any system. So here's my system operating in a cycle. And so what I put an X across this, it says, so you see what I'm doing here in this schematic. I'm transferring heat, Q dot L, from a low temperature reservoir, that's like inside your refrigerator. I'm trying to do I've got some equipment that's transferring heat up to a high temperature reservoir. That's like the back of your refrigerator. That's your kitchen. This is, and that's it. That's it. It says the sole result. So you see, I've labeled on my schematic, W.net is 0. This is impossible. So it is impossible to achieve this, period. No matter how much you wish or hope or want, or no matter how much positive thinking you can do, you can't pull off the left-hand side schematic. That's the statement of the clause. That's the schematic version of the Clausius statement. Let's look at the right-hand side, which I've put a check. This is possible. Okay. I've got a system operating in a cycle, like your refrigerator. Okay. I'm transferring heat from cold to hot. But what I'm doing is, look at my less than 0. I've got to invest some power. I've got to invest some work to make this happen. So this is possible. And this is an example of a refrigerator. Okay. I'm going to dwell on this instead of going to the next slide immediately. Let me recap just a little bit. Clausius statement. Clausius statement says, you can't transfer heat from cold to hot, and that's it. Okay, so that's the schematic statement of the Clausius statement of the second law. But you can transfer heat from cold to hot if you invest some work. And there you go. Let's move on. The second statement is called the Kelvin-Planck statement. These were people, Kelvin and Planck, Max Planck. These were people. Okay, so let me read the words clipped right out of your book. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work, W net, to the surroundings, lifting a weight, while receiving energy by heat transfer from one single heat thermal reservoir. Okay, a lot of words. Here's what the sketch looks like of the Kelvin-Planck statement. So here's my system operating in a cycle. Okay, I'm producing net work. I'm lifting a weight at a certain rate here in my sketch. And I'm transferring heat from a high temperature reservoir. The Kelvin-Planck statement, the statement of the second law says, this is impossible. You can't operate in a cycle. Okay, that's important. That's an important word. You cannot operate in a cycle and turn heat directly into work. So you cannot have a power plant that does this. Okay, it's simply impossible. Okay, so as much as you would love for this to happen, and in many cases we'd love for it to happen, you can't say anything is possible and make this happen. It is impossible. You say, wait a minute. We do see power plants, so why is that possible? Well, here's a schematic of a power plant. So this is possible. We are turning heat into work, or rate of heat transfer into net power. We're doing that. But what else must we do? We must reject some measure of heat to the low temperature, to the surroundings, to a low temperature reservoir. So we've got a high temperature reservoir, like hot exhaust gas, a heat source, hot, okay. Low temperature heat source, kind of like the surroundings, okay. So the Kelvin-Planck statement, it doesn't say how much, it doesn't talk about numbers, but it says you can't operate in a cycle and turn all of your heat transfer totally into work. You've got to reject some measure of heat. Okay, so I'm not going to race to the next slide. I'm going to maybe let you look at this slide a little bit, okay? And maybe let it soak in. Kelvin-Planck statement. When I'm teaching the class, I do not require students to memorize the Kelvin-Planck statement, okay? I don't require that. But students do need to understand why the right-hand side is possible. It's a power plant. And why the left-hand side is impossible. That's the key. Okay, the third statement of the second law, and it's called the entropy statement. And I've clipped this out of your book as well. It says, so this is also a statement of the second law. It's impossible for any system to operate in a way that entropy is destroyed. Entropy, S. Impossible for any system to operate in any way where entropy is destroyed. In other words, a measure of disorder is destroyed, okay? Now, here's what this says in an equation. Let me jump down to the bottom first in my green text box. Sigma, this is not 6, by the way. It's Greek letter sigma, so don't say 6. Greek letter sigma. Sigma is called entropy production in your textbook. Your textbook does a superb job of developing this concept, but sigma is called entropy production. So the opposite of entropy production would be entropy destruction. See how that would be opposite? Okay. Entropy destruction would be the opposite of entropy production. Okay. And so here is an equation statement of the second law. Sigma is greater than or equal to 0 for any system undergoing any process. In other words, the entropy production for any process is always greater than or equal to 0. So that's an important thing to recognize. So your textbook does a great job of developing this process-specific value called entropy production. It is not it's not a property. Sigma is not a property. It's a measure of the way a process proceeds. And so sigma is greater than or equal to 0 for any system undergoing a process. That is a great way to say the entropy statement. It's a super way to say the entropy statement, which is a statement of the second law. It's the third statement of the second law. Well, we've reached the end of this video. Okay. And so what have we learned from this video and a little bit before? Entropy is a property. Visualize entropy as a measure of disorder. Okay. The higher the disorder, the higher the entropy. And the more ordered, the lower the entropy. Okay. Another thing is that based on that entropy statement, the third statement, it says entropy is produced, sigma greater than 0. Entropy is produced whenever something irreversible occurs. Entropy is not produced. Entropy stays constant. The order of things or the disorder of things stays constant when something reversible occurs. Okay. But the important thing is entropy is produced whenever something irreversible occurs. Okay. So when it's time to get something in order, the usual result is that something somewhere else gets disordered. Have you noticed that in your life? When you're assigned to get something in order, it seems like something else gets discombobulated. Something somewhere else gets disordered, or the surroundings stay the same. That's the best you can hope for. So when you and we are assigned to get things in order, the best can happen is that everything stays the same and you've got something ordered. That would be like reversible. But in most cases, the irreversible situation, something somewhere else gets disordered when you've gotten something ordered. I hope that helps. Okay, it turns out that you're seeing that I'm kind of enjoying doing this, right? You can enjoy doing this stuff once you get a good starting understanding of this stuff. And the better you understand it, the more fun you have. And so let me encourage you to hang in there. Try to get these fundamentals. So far in the Chapter 5 videos, if you're stepping through them one by one, you say, we haven't put pencil to paper. We haven't crunched any numbers. And that can be uncomfortable sometimes. And so the early parts of Chapter 5 is very much introduction of concepts and setting down some rules regarding the second law. Thing like sigma is greater than or equal to 0. In other words, that's that third statement of the second law. So I hope that helps. I hope that encourages you to keep going with this. And I can assure you that once we get near the middle and end of Chapter 5, we're going to be able to quantify. And then when we get into Chapter 6, we're going to really be able to quantify.